Lecture 11.7, More on Hyperbolic Functions. Today we'll look at a few other aspects of hyperbolic functions. Let's look at the Taylor series for y equals sinh x. We can generate it from scratch. We use the definition sinh x equals e to the x minus e to the negative x over 2. And what we want to generate is the Maclaurin series, or the Taylor series centered at 0. If we start with f of x and plug in 0, we get f of 0 equals 0. Taking the first derivative, the negative exponent comes down and cancels the negative sign in the middle. We get e to the x plus e to the negative x over 2. And when we substitute 0 for x, we get 1. For the second derivative, we have e to the x minus e to the negative x over 2. Evaluated at 0, we get 0. The third derivative is e to the x plus e to the negative x over 2. And the third derivative at 0 gives us 1. Finally, the fourth derivative is e to the x minus e to the negative x over 2. And the fourth derivative at 0 is 0. Now, substituting into the standard equation, we get sinh x equals 0 plus 1 times x plus 0 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 0 over 4 factorial x to the fourth, etc. Every other term drops out, and we get sinh x equals x plus x cubed over 3 factorial plus x to the fifth over 5 factorial plus x to the seventh over 7 factorial, which is equal to the summation from n equals 0 to infinity of x to the 2n minus 1 over 2n plus 1 factorial. This is the same as the series for y equals sin x, except that the terms do not alternate. We could also have generated this series by combining known series. Sinh x equals e to the x minus e to the negative x over 2 is just 1/2 times the difference between the series for e to the x and the series for e to the negative x. So we subtract and get sinh x equals 1/2 times 0 plus 2x plus 0 plus 2x cubed over 3 factorial plus 0 plus 2x to the fifth over 5 factorial. Canceling a 2 gets us back to the series for sinh x. This is how we could graph y equals sinh x by hand. Since sinh x equals e to the x minus e to the negative x over 2, we start with a graph of y equals e to the x. E to the 0 is 1, so we put a dot at 0, 1. And e to the 1 is e, or about 2.7. So we have a dot at 1 and 2.7. Now we can sketch in our exponential graph. Y equals e to the negative x is a y-axis reflection of our previous graph. but our definition includes a negative sign. So y equals negative e to the negative x is now an x-axis reflection. So it's an x-axis and a y-axis reflection. The definition of sinh x is just the average of e to the x and negative e to the negative x. So we average our two curves. This gives us the graph of sinh x. Here are the basic three hyperbolic functions graphed on the Cartesian coordinate system. Y equals sinh x, which we just did. Here's y equals cosh x. And y equals tanh x. There's not an obvious connection between the hyperbolic graphs and standard trig graphs. Now we will look at a parametric graph. First, remember that trig functions make a circle when graphed parametrically. If we graph x equals cosine t and y equals sine t, we get a circle with radius 1. This makes sense if we look at this identity. Starting with the identity cosine squared x plus sine squared x equals 1, which we could also have written as cosine squared t plus sine squared t equals 1. We can substitute to get x squared plus y squared equals 1, which is the equation of a circle with radius 1. To graph the hyperbolic functions, x equals cosh t, y equals sinh t, we can start with the identity cosh squared x minus sinh squared x equals 1, which we could also have written as cosh squared t minus sinh squared t equals 1. We can substitute to get x squared minus y squared equals 1, which is the equation of a hyperbola. So graphing x equals cosh t, y equals sinh t, we get half a hyperbola. These hyperbolic functions make half a hyperbola, hence the hyperbolic in hyperbolic functions.